Hello everyone, today I am going to make an audio recording for visually impaired student of Pradeep Inorganic Chemistry, Volume 2 by Dr. K. Bhasin. Today's topic is acid and bases. Arrhenius concept of acid and bases. Arrhenius, a Swedish chemist, was the first to define acids and base in aqueous solution. According to Arrhenius, an acid is defined as a substance which contains hydrogen and which when dissolved in water gives hydrogen ions. Accordingly, all mineral acids like HCl, HNO3 and H2SO4 containing hydrogen when dissolved in water dissociate completely into hydrogen ions H plus S. HCl give rise to H plus Cl negative. HNO3 give rise to H plus NO3 negative. H2SO4 give rise to 2H plus SO4 2 negative. Arrhenius named this acid which dissociate completely in water as strong acid. There are other acids like acetic acids, carbonic acids and phosphoric acids which when dissolved in water do not dissociate completely into ions. As a result, an equilibrium is set up between the ions and the undissociated acid molecules as shown below. CH3COOH at equilibrium attain H plus CH3COO negative. H2CO3 give rise to 2H positive plus CO3 2 negative. S3PO4 at equilibrium attain 3H positive plus PO4 3 negative. Arrhenius named this acid as weak acid. According to Arrhenius, a base is a substance which contains hydroxyl group and which when dissolved in water gives hydroxyl ions. The substances like NaOH and QH which when dissolved in water dissociate completely to give hydroxyl ions OH negative as. NaOH give rise to Na positive plus OH negative. KOH give rise to K positive plus OH negative. Arrhenius named these bases which dissociate completely in water as strong bases. There are substances which do not completely dissociate into hydroxide ions. Arrhenius named these substances as weak base. For example, substances like NH4OH, MgOH2, AlOH3 do not dissociate completely to give OH negative ions and can be written as NH4OH NH4 positive plus OH negative. MgOH2 dissociate Mg2 positive plus 2OH negative. AlOH3 dissociate Al3 positive plus 3OH negative. Hydrogen ions obtained from the acid and hydroxyl ions obtained from the base combine together to form unionized water. Arrhenius described this combination of H positive and OH negative ions as neutralization reaction. Example, NaOH give rise to Na positive plus OH negative. HCl give rise to H positive plus Cl negative. Combine both reaction and Na positive plus OH negative plus H positive plus Cl negative. Na positive plus OH negative plus HO positive plus Cl negative give rise to Na positive plus Cl negative plus H2O. H positive plus OH negative give rise to H2O. Arrhenius concept is very simple to apply and explain a number of phenomena like neutralization, hydrolysis of salt, strength of acid and base. However, there are certain limitations which are described below. Arrhenius concept of acid and base is applicable only in aqueous solution. This concept fails to explain the acid or base behavior substance in non-aqueous medium such as liquid ammonia, liquid sulfur dioxide, alcohol, etc. Second, Arrhenius concept fails to explain the acidic character of substance like CO2, SO2 and SO3, etc. and basic character of substance like NH3, Na2, CO3, CaO, etc. Third, Arrhenius concept also fails to explain the reaction between an acid and a base in the absence of water. For example, NH3 gas plus HCl gas give rise to NH4Cl solid. Na2 solid plus SO3 gas give rise to Na2SO4 solid. Although Arrhenius' concept of acid and base suffers from a number of limitations, yet the concept is very useful and informative for an elementary approach. Bronsted-Lowry concept. Arrhenius' concept of acid and base was further improved by Bronsted and Lowry. Both Bronsted and Lowry in 1923 incidentally introduced the same definition for acids and base. According to Bronsted-Lowry concept, An acid is a substance which can donate a proton, whereas a base is a substance which can accept a proton. In other words, an acid is a proton donor, whereas a base is a proton acceptor. As a result, Lowry-Bronsted concept is sometimes called the proton donor acceptor concept. It can be represented as acids at equilibrium attain H positive plus base proton donor. Base 2 plus H positive at equilibrium attain acid 2 proton acceptor. According to Bronsted-Lowry, a neutralization reaction involves the release of the proton by an acid and the acceptance of that proton by a base. For example, the reaction between HCl and NH3 to form the salt ammonium chloride can be represented as. The curved arrow shows how electron must rearrange to result in the transfer of hydrogen atom from the acid to a base. The unshared pair of electron on the nitrogen of ammonia is attracted by the partially positive charge on the hydrogen in the polar hydrogen chloride molecule. A comparison of the structure of the reactant and product showed that the hydrogen atom, which was bonded to chlorine in the reactant, is bonded to nitrogen in the product. Thus, a proton has been transferred from chlorine to nitrogen. To act as a Bronsted-Lowry base, a species must have at least one unshared pair of valence electron so that it can form a covalent bond to the proton. To act as a Bronsted-Lowry acid, a species must contain at least one hydrogen atom that is attached to an atom that is more electronegative than hydrogen. In this case, HCl loses a proton and is an acid. Ammonia accepts a proton from HCl and is a base. It is important to note in the above example that water acts as a base with respect to hydrochloric acid and sulfuric acid. Interestingly, water acts as an acid with respect to ammonia. Such a substance which acts both as an acid as well as a base is called amphoteric or amphiprotic substance. Conjugate acid-base pair. HCl being an acid donates a proton and forms Cl negative, whereas ammonia being a base accepts a proton and forms ammonium ions. Now the chloride ion has a tendency to accept the proton, whereas ammonia ion has a tendency to donate a proton. In other words, an acid donates a proton and becomes a base, and a base accepts a proton and becomes an acid. Thus, a base formed from an acid is regarded as the conjugate base of the acid. Similarly, the acid formed from a base is called the conjugate acid of the base. In the example above between HCl and NH3, Cl negative is the conjugate base of HCl and NH4 positive is the conjugate acid of the base NH3. Acids and bases that are related by the loss or gain of H positive ions are called conjugate acid-base pair. Thus, Cl negative and HCl, NH4 positive and NH3 are conjugate acid-base pair. We can represent the acid at equilibrium attain conjugate base plus H positive. It clearly indicates that an acid base reaction would involve two acid and two base. These acids and base are called conjugate pairs. In above example, HCl is an acid since it donates a proton and Cl is its conjugate base. Water accepts the proton and hence is a weak base. Thus H3O ion is the conjugate acid. A strong acid has a weak conjugate base and vice versa. A substance is capable of showing acidic character only if the other substance is capable of accepting the proton, that is a base. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. However, HCl is not an acid in benzene because benzene does not accept H positive ion from HCl. Second, not only neutral molecules but cations and anion may act as acid or base. Third, both Arrhenius and Bronsted-Lowry concept require an acid to be source of proton. Thus, all Arrhenius acids are Bronsted-Lowry acids. Fourth, according to Arrhenius, a base is a substance which gives OH negative ions in the solution. NaOH gives rise to Na positive plus OH negative. Whereas according to Bronsted-Lowry, a base is a substance which can accept a proton. For example, CO3 negative plus H positive give rise to HCO3 negative bicarbonate ion. Carbonate ion CO3 negative cannot give OH negative ions in aqueous solution. It therefore cannot be an Arrhenius base. Thus, all Bronsted-Lowry bases are not Arrhenius bases. Limitations of Bronsted-Lowry concept. Although Bronsted-Lowry concept could explain the shortcoming of Arrhenius concept, yet it could not answer some of the well-established reactions. For example, it cannot explain. The first is the reaction between acidic oxide like CO2, SO2 and SO3 with a basic oxide like CaO, BaO and MgO which take place even in the absence of water. For example, CaO plus SO3 give rise to CaSO4. Clearly, in the reaction between CaO and SO3, there is no proton transfer involved in the reaction. Second is the acidic nature of compounds like BF3, FeCl3 and AlC3. Lewis concept of acid and base. Jean Lewis in 1923 proposed a more general definition of acids and base which is based upon the donation and acceptance of electron pair. According to Lewis' concept, an acid is a substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor. It means that a substance which has vacant orbital to accommodate one or more pairs of electrons can act as a Lewis acid. On the other hand, a base is an electron pair donor. It means that any substance with unshared pair of electrons can behave as a Lewis base. Thus, the acid-base or neutralization reaction involves the formation of a coordinate bond between the electron pair donor and the electron pair acceptor. For example, the reaction between boron trifluoride BF3 and ammonia NH3 is a typical Lewis acid-base reaction. This concept, Lewis acids are classified as first molecules having central atom with incomplete octet of electron. Boron trichloride, boron trifluoride, aluminum trichloride, etc. are acids of this type. It is clear that central boron and aluminum atom have only 6 electrons. Second is simple cations. All the cations are short of electron and can behave as Lewis acids. Large size cations like Na positive, K positive, Ca2 positive and Ba2 positive etc. behave as weak Lewis acid. This is because these have little tendency to accept electrons. On the other hand, small size cations such as H positive, A, G positive, Li positive ions have a strong tendency to accept the pair of electrons and a strong Lewis acid. In addition, highly charged cations have a higher tendency to accept electron pair related to lower charged cations of the given metal. For example, SNO4 is a stronger Lewis acid than SN2 positive. Molecules in which central atom has available d orbitals and may acquire more than 8 electrons. Compounds such as AlCl3, SiF4, SnCl4, SbF5 and SO3 are Lewis acid, whereas the central metal atom can expand its valence shell. Fourth is molecules with a multiple bond between atoms of dissimilar electronegativity. Carbon dioxide represents an interesting example of a double bond between carbon and the more electronegative oxygen atom. Oxygen, being more electronegative, has a tendency to attract the shared pair of electrons more towards its CO2. As a result, it requires positive charge on the carbon atom and becomes electron deficient and attached with oxygen of the hydroxide ion. Similarly, sulfur trioxide acts as Lewis acid towards water. Lewis base. According to this concept, Lewis base may be classified as one of the following types of substances. Negatively charged anion species. All the negative charged species are Lewis base because they are rich of electron and have a strong tendency to donate electron pair. Common example are Cl negative, O2 negative, OH negative, NH2 negative, etc. The greater the charge density on the anion, the stronger is the base. Second, neutron molecules with one or more than one unshared pair of electrons. Molecules with unshared pair of electrons act as Lewis base. For example, NH3, H2, S2O, R2O and R2C double bond O act as electron donor. Third, alkenes and alkynes with multiple bonds also form coordinate bond with metal ions in organometallic compounds. Acid-base reaction according to Lewis concept. Some of the typical acid-base reaction involve the formation of coordinate bond between a Lewis acid and Lewis base as summarized below. Combination between H positive and NH3. Now, Lewis base plus Lewis acid give rise to ammonium ion. Lewis acid-base concept discussed above is widely used because of its simplicity in understanding many acid-base reactions. In spite of its wider application than Arrhenius and Bronsted-Lowry concept, it has several disadvantages which are discussed below. First, Lewis concept is too general and consider all reactions forming a coordinate bond to be acid-base reaction. This is, however, not true always. According to Lewis concept, some of the transition metals that form compounds with carbon monoxide such as NiCO4, FeCO5, etc. are acid-base reaction, which is not correct. Second is formation of a coordinate bond between an acid and a base is the basis of Lewis concept. However, the well-known acids like HCl, HNO3 and H2SO4 do not form any coordinate bond with the bases such as NaOH or KOH. Accordingly, HCl, HNO3 and H2SO4 should not be regarded as acid according to Lewis concept. Third is Lewis concept does not give any uniform scale of acid and basic strength. Lux flood concept of acid and base. A new concept of acid and base was proposed by Lux in 1939. This concept was further extended by Flood. According to Lux flood, an acid is a substance which can accept an oxide ion, where a base is any substance which gives up oxide ion. Lux flood bases can be represented as CO at equilibrium attained Ca2 positive plus O2 negative. An acid can be tentatively represented as SiO2 at equilibrium attained Si4 negative plus 2O2 negative. Lux flood acid base reaction can be represented as SiO2 plus CaO give rise to CaSiO3 salt. According to Lux flood concept, substances that show tendency to lose as well as gain an oxide ion are termed as amphoteric. Zinc oxide represents an interesting example of amphoteric character. For example, zinc oxide can lose O2 negative to form Zn2 positive ion, in addition to zinc oxide gaining an O2 negative to form ZnO2 2 negative zincate ion. Similarly, Al2O3 can behave both as an acid as well as a base in Lux flood science and hence act as amphoteric. This concept of Lux flood is very useful at high temperature, especially in glass ceramic industry and metallurgical operation. The concept of Lux flood can also be extended to halides and sulfides. For example, AlF3 plus 3 NF give rise to Na3AlF6CS2 plus Na2S give rise to Na2CS3. Usanovich concept of an acid and a base. Usanovich concept of acid and base is very general and takes into consideration all the concept of acids and base proposed by Arrhenius. Lowry, Bronsted and Lewis acid. In addition, Usanovich concept includes all oxidizing agent as acids and all reducing agent as base. Thus, according to Usanovich concept, an acid is a substance that react with the base, second gives up cation, and third is accept anions or electron. Similarly, Usanovich concept defined as a base is substance that react with an acid, gives up anions or combines with the cations. Usanovich concept is very useful as it classifies all examples of acid and base together. However, it is too general. This is because it considers even the oxidation reduction reaction as acid-base reaction. Solvent system concept. The solvent system concept of acid and base was postulated by Caddy Astley in 1928. It is an extension to the Lowry-Bronsted concept and is applicable to both protonic as well as a non-protonic solvent. According to this concept, an acid is a substance which either by direct dissociation or by the interaction with the solvent gives the cationic character of the solvent. A base is substance which either by direct dissociation or by the interaction with the solvent gives the anionic character of the solvent. The characteristics cation and anion of the solvent are the ions produced during the autoionization. The prefix auto means itself. To illustrate this concept, let us consider the autoionization of the some protonic and non-protonic solvent. Hence, H2O plus H2O give rise to attained equilibrium, give rise to acid H3O positive plus OH negative. For example, HCl behaves as an acid in water solvent as it gives the cationic characteristics of water. Similarly, NH3 acts as a base in water as it gives the anionic character of OH negative of water. It is important to note that acetic acid behaves as an acid in water as it produces the cationic character of water. CH3COH plus H2O at equilibrium attained give rise to H3O positive plus CH3CO negative. Acetic acid behaves as a base in sulfuric acid as it produces as the anionic characteristic of the solvent sulfuric acid. CH3COH plus H2SO4 at equilibrium attains CH3COO S2 positive plus HSO4 negative. Urea dissolves very rapidly in water and gives neutral solution. However, urea dissolves in liquid ammonia and behaves as an acid because it gives the cationic characteristic of the solvent ammonia. Similar to Arrhenius concept, neutralization reaction may be represented as the combination of cationic characteristics of the solvent with ionic characteristics of the solvent to form the solvent molecule. Some of the neutralized reactions in various solvents are given below. Liquid ammonia NH4Cl plus NaNH2 at equilibrium attain NaCl plus 2NH3. It is important to note that neutralized according to solvent system concept is the reverse of autoionization reaction. Types of solvent. Types of solvent. Solvents are classified in a number of ways on the basis of their physical and chemical properties. Broadly, there are three ways in which solvent can be classified. First, protonic and aprotic solvent. Solvents which contain hydrogen and can lose hydrogen in the form of proton are called protonic solvent. Common example of protonic solvents are H2O and NH3, H2SO, HF, etc. Solvent from which hydrogen cannot be obtained in the form of proton are called aprotic solvent. Common example are CS3CN, C6H6, etc. Solvent from which hydrogen cannot be obtained in the form of proton are called aprotic solvent. Common example are CH3CN, C6H6, etc. Solvent like N2O4, SO2 and CCl4 are also called aprotic solvent. Second, acidic, basic and amphiprotic solvent. Solvent which have a strong tendency to give proton are called acidic solvent. Common acidic solvents are H2SO4, HF, CH3COOH, etc. Solvents which have a strong affinity for proton are called basic solvent. Basic solvent are ammonia, hydrazine, pyridine, etc. Solvent which display both acidic and basic properties are called amphiprotic solvent. Example of amphiprotic solvent are water, methyl alcohol, etc. Third, ionizing and non-ionizing solvent. Solvent which undergo self or auto-ionization are called ionizing solvent. Typical example of ionizing solvent are water, ammonia, hydrogen fluoride, sulfur dioxide, etc. H2 at equilibrium attain H3O positive plus OH negative. Solvents which do not ionizing are called a non-ionizing solvent. Typical example of non-ionizing solvent are benzene, carbon tetrachloride. Such solvents are non-polar and have low dielectric constant. Relative strength of acid. The strength of protonic acid can be compared easily by the tendency of the acid to give protons. Protonic acid like HCl, H2SO4, HNO3 ionize completely to give protons, whereas acids like CH3, COH, HF and HCN ionize incompletely to give protons. The acid which ionize either completely or to a very large extent are named strong acid. On the other hand, acid which ionize to a smaller extent are named weak acid. Thus, protonic acid namely HCl, H2SO4 and HNO3 are strong acid, whereas CH3COH, HF and HCN are weak acid. It is the extent of ionization of an acid which measures the strength of the acid. Let us consider the ionization of an acid Ha, which is represented as Ha at equilibrium attain H positive plus A negative. Equilibrium constant K for the reaction is written as Ka is equal to H positive A negative divided by Ha, where H positive A negative and Ha are the concentration of H positive A negative and the undissociated acid. HAK is known as the dissociation constant or ionization constant of the acid. The magnitude of a K measures the relative strength of the acid. The stronger the acid, the larger is the value of Ka. It is convenient to use the term pKa to express the dissociation of an acid. pKa is equal to minus log Ka is equal to 1 by log Ka. A larger value of pK means that the acid is little dissociated. It implies that the acid is weak. Thus, larger the value of pK, the weaker is the acid. Trends in acid strength. We have learned that the relative strength of acid in aqueous solution can be easily expressed in terms of a pK value. The higher the value of pK, the weaker is the acid and vice versa. A comparison of a pK value of binding hydrides reveals that on moving from left to right across a period, the strength of the binding acid increases. For example, the acidic strength of the binding acids along the second period decreases as HF greater than H2O greater than NH3 greater than CH4. It can be easily explained on the basis of electronegativity of the element as one moves from left to right along a period. Fluorine more electronegative than oxygen, than nitrogen, than carbon. It is very important to note this side does not change greatly across a period. With increase in the electronegativity of the central atom, the tendency to pull the electron pair from the hydrogen increase. This facilitates the release of hydrogen in the form of proton and makes the hydride more acidic in character. On similar consideration, we can explain how the acidic strength of binding hydrides of the third period decreases as HCl greater than H2SO greater than PST. A comparison of the pK value of binding hydrides reveals that the relative strength of the acid increases as one moves down the group. As inspection of the pK reveals that hydrogen fluoride is a weaker acid than hydrogen iodide. The relative strength of halogen group 7A decreases as HF less than HCl less than HBr less than HI. Group 6A, the strength of the acid increases as one move down the group. What is a weaker acid than hydrogen telluride? The actual order of the acidic strength down the group in the periodic table cannot be explained solely on the basis of electronegativity consideration. For example, in 7, fluorine being the most highly electronegative element should pull the electron pair towards itself in HF. As a result, the release of hydrogen in the form of proton should be highly facilitated, making HF is the strongest acid. In fact, HF is the weakest acid. The effect of increase in the size of the atom is decrease in the electronegative value of the central atom. A proton can be more easily removed from a binding hydride in which the central atom is bigger in size as compared to an atom which has smaller size. The Hi can release the proton more easily than HF. As a result, Hi is the strongest acid, whereas HF is the weakest acid among the halogen acids. The acidic strength leveling effect. The strength of an acid or a base depends largely on the nature of solvent used for its dissolution. Let us consider the dissolution of hydrogen chloride in three different solvents: ammonia, water, and sulfuric acid. One can clearly see that HOClO is a strong bronzed acid in NH3, a weak base in water, and a strong base in H2SO4. The acidity and basicity of a protein solvent plays an important role in choosing a solvent for a chemical reaction. The strongest acid which is available in protic solvent is that which results from the self-ionization of the solvent. Likewise, the strongest base available is that which results from the self-ionization of the solvent. It means that all the strong bases are level to the strong of OH negative ions on the reaction with the water. In other words, solvent water level all the strong base to the strength of OH negative ions. For example, when sodium hydride NaH is added to water, a vigorous reaction occurs with the brisk evolution of hydrogen gas and the resulting solution is found to be a solution of sodium hydroxide. Similar reaction occur when other bases like NaNH2 and sodium ethoxide are added to water. In order to compare the relative strength of strong acid and base, the selection of the solvent is very important. The solvent selected should be such that it ionizes the strength acids and base to different extent. Such a solvent which ionizes the acid and base to different extent is called a differentiating solvent. Acetic acid can be used as a differentiating solvent because strong acids like HClO4, Hi, HBr, HNO3 and HCl will ionize to different extent in acetic acid. Acetic acid is a poor proton acceptor. Perchloric acid reacts completely, that is protonates completely acidic acid as other acids do not react completely because of incomplete protonation of acetic acid by this acid. On the basis of relative strength of different ionization of these acids in acetic acid, arranged in the order. Acetic acid is the leveling solvent towards base such as Ca negative, H negative, OC2H5 negative, and NH2 negative. This is because acetic acid react with the base and level them to strength of acetate ion. How strongly basic solvents such as liquid ammonia act as differentiating solvent towards base. It may be concluded that acidic solvent tends to differentiate between acids and level of bases, whereas basic solvent tends to differentiate between base and level of acids. Strength of oxo acids. The hydroxide of the reactive metal are ionic compounds and are strong base. However, hydroxide of the non-metals are molecular compounds and are acidic. The oxo acids can also be considered as the derivatives of water and can be represented by the formula EOH. E is the non-metal which determines the acidity of the compound. It depends upon the size of the atom E, electronegativity of the atom E, and inductive factor of the substituent present on E. A small and highly electronegative atom E will pull the shared pair of electrons between E O bond more towards itself. In turn, oxygen will pull electrons from hydrogen atom in the OH bond and makes the proton to dissociate easily. This makes the compound EOH to behave as an acid. Thus, the higher the electronegativity of E, the more easily the proton is lost, and consequently stronger is the oxo acid. The acidic character of the oxo acid of halogen decreases in the given order from pKa values. The acidity of the oxo acid are related to the number of additional oxygen atom attached to the atom E. In this compound, the acidic will increase the oxidation number of the atom E in the series of oxo acid of chlorine. The acidic strength increases in the following order. All these acids have only one protonated oxygen, that is only one OH group. Perchloric acid has 3, chloric acid has 2, and chloric acid has 1 atom additional oxygen atom. This additional oxygen atom stands to withdraw more electron density from the hydrogen through the intervening chlorine atom. OH bond increase more in case of acids containing larger number of oxygen atom. Oxo acid without extra oxygen are weak, oxo acid with one extra oxygen atom moderate, and oxo acid with two or more extra oxygens are strong acid, increasing the acidic strength of HCl4 greater than HCl3 greater than HCl2 greater than HClO. Strength of Lewis acid and base. A solvent plays an important role on the strength of Lewis acid and base. A Lewis acid on hydrolysis may produce an acid stronger than the Lewis acid itself. For example, boron trichloride, which is a Lewis acid, undergoes hydrolysis with the evolution of hydrogen chloride. The sequence of first step involved in the hydrolysis are outlined below. The first involves the attack of water molecule on the vacant 2p orbitals of boron. A lone pair of electrons from what is donated to the empty orbital of boron with the formation of a coordinate bond. The second step involves the loss of one HCl molecule. In doing so, one of the chlorine BSCl3 is replaced by one OH group. The third step involves the repetition of the above step till all the chlorines are replaced by hydroxyl group and one get boric acid as 3BO3. And the interesting example where the role of solvent is greatly appreciated is the hydrolysis of silicon tetrachloride to afford silicic acid. The distinguished feature in the hydrolysis of boron trichloride and silicon trichloride is the presence of vacant 3d orbital in case of silicon. The mechanism of a system accepting that the water molecule attacks the vacant 3d orbital of silicon, forming an adduct involving coordinate bond between silicon and oxygen. Thus, adduct form losses HCl molecules in steps. Chlorine atom are replaced by OH group, yielding finally silicic acids. Thank you.